Today's artificial intelligence feels incredibly close to human cognition. Large language models write complex software, pass the bar exam, and hold fluent, intelligent conversations. Yet these same advanced systems routinely fail at basic logic puzzles. They struggle to comprehend physical reality, lacking the everyday common sense that a house cat possesses. Think about how we learn. A 17-year-old can safely drive a car after 20 hours of practice. Meanwhile, a machine learning model requires insane amounts of trial and error, running through thousands of simulated crashes just to understand a steering wheel. Despite their massive commercial utility as text generators, our top AI models possess a severely shallow grasp of how the physical world actually works. Meta's chief AI scientist, Yann LeCun, argues that scaling up our current models is a dead end for achieving human-level artificial general intelligence. The limitation lies in their underlying design. Current systems are autoregressive. This means they operate by calculating the statistical probability of the next literal piece of data in a sequence over and over again. This mechanism makes them brilliant at continuing a pattern, but because they are just extending a sequence, they are essentially speaking without thinking. They don't draw from a robust representation of reality. Human cognition works differently. We build internal, abstract models of our environment. When you drop a glass, your brain anticipates the physical consequences before it even hits the floor. Simply generating the next text token cannot replicate this physical intuition, and it cannot handle complex, uncertain futures where multiple outcomes are possible. If generating token-by-token sequences won't build common sense, what architectural blueprint will? Traditionally, when researchers train a visual AI, they use a generative approach. They hide a piece of an image and force the system to guess the exact missing pixels. This forces the AI to waste massive computational power on irrelevant surface details. It strains to reconstruct the exact texture of a tree's bark, rather than grasping the concept that it is looking at a tree. A new framework called the Joint Embedding Predictive Architecture, or JEPA, shifts the learning goalpost entirely. JEPA abandons raw data reconstruction. Instead, it learns to predict the meaning, or the abstract representation, of what is missing. Operating in this abstract hidden space allows the AI to filter out noise and learn the underlying semantic rules of the world much faster. By removing the burden of literally drawing missing pieces, JEPA builds a robust model of concepts rather than just a mimicry of textures. Here is how it functions. The system starts with a context encoder, a neural network module that looks only at the visible, known parts of the data. Running parallel to this is the target encoder, which processes the hidden or future part of the data that the model eventually needs to predict. Both encoders funnel their information into a central shared space, sometimes called an embedding space. Here, the visible context and the hidden target are converted into the exact same abstract format so they can be compared. Next comes the predictor. It takes the context data and attempts to guess the abstract state of the target. The system learns not by matching pixels, but through a training loop that minimizes the mathematical distance between its prediction and the real target embedding. This separation of components creates a model that continuously evaluates relationships and structures, upgrading how an AI analyzes information, from mere pattern matching to actual semantic understanding. Abandoning literal prediction frees the AI to handle uncertainty. Instead of getting stuck guessing a single outcome, it can represent multiple plausible futures at once. This paves the way for a hierarchical world model, a structure that allows an AI to reason across different timescales simultaneously. At the base level, JEPA predicts fine-grained local dynamics. These rapid calculations handle immediate physical control, like placing a cup on a table. Simultaneously, it predicts coarse-grained abstractions, higher-level thoughts needed for long-horizon planning, like navigating across an entire city. By combining explicit actor modules that make decisions with these latent variables, JEPA steps out of a reactive loop and achieves deliberate multi-step reasoning. This table shows the scale of Llama 2 models, with the largest reaching 70 billion parameters trained on 2 trillion tokens. Autoregressive language models of this brute force size are not going away. They remain highly profitable tools designed to accelerate software development and process text. But infinitely scaling these models and feeding them more written language will never spontaneously result in a genuine understanding of physical reality. Objective-driven world models, built on architectures like JPA, offer the rigorous blueprint required to break through the current limitations of generative AI. The ultimate goal of artificial intelligence is machines with memory, reasoning, and common sense. And those qualities won't be achieved by merely generating the next word. They will be achieved by learning to predict the world.